Let's begin by turning on our oscilloscope and letting it boot up. After it's booted up, I like to push the default setup button because I don't know what it was used for last, and it generally retains its previous settings. We also need to turn on the function generator. Make sure all these buttons are out. I'd put the output somewhere at about halfway and select the square wave function. Set the function generator to the 500 range and adjust the frequency knob until it's, 3 to 400 hertz. Notice that there's no change in the display on the oscilloscope. This is because the response time for our circuit is much smaller than the period of the square wave on the function generator. Switch the function generator to the 5000 Hertz range. Now the frequency of the function generator is quick enough to display a few periods at the default setting of the oscilloscope. Notice that the shape of the curve hasn't really changed. What we are observing is the voltage across the capacitor. We are using the square wave on the function generator to mimic an on-off switch for charging and discharging the capacitor. You can look at a higher frequency from the square wave and adjust either the voltage or the time settings just to experiment. If the frequency of the square wave is too fast, there's no time for the capacitor to fully charge or discharge. And that's what we see here. Go back to the original 500 range on the frequency. Adjust the volts per division knob until you have a full signal on the screen. I'm going to adjust the output voltage slightly, and I'm going to adjust the vertical position so that the top and bottom of my signal fall on convenient lines, making it easy to measure. I count 1, 2, 3, 4, 5, 6 divisions. I want to know how long it takes to go from the bottom up 3 divisions. If I were to try to measure the time it takes to go up 3 divisions on this time setting, it happens in such a small amount of time compared to the time setting that I could not measure it accurately. So I'm going to stretch out my signal by changing the time setting. Notice that I have 2 parts of the curve here. It's a triggering issue and you may not be able to solve it. My goal at this point is to stretch out the time signal as much as possible while still being able to show the curve go from the baseline to 3 divisions up from there. You may have to do a horizontal adjustment to keep the baseline still visible. This is stretched out pretty far. I have several time divisions for it to go up 3 voltage divisions. Let me try a little bit more and see if I can fit that on the screen. It looks like it almost fits, but it's just barely under the 3 divisions above mark. So I'm going to go back to the previous setting. Now I need to count the time divisions. 1, 2, 3, 4, 5, about 5.5 measure as accurately as you can. And then you need to multiply times the time per division, which is up here at the top of the oscilloscope. We have just measured the time it takes for the capacitor to go from uncharged to halfway charged. We're going to call this T1/2. Your lab will explain how the time constant, represented by the Greek letter tau, relates to the time it takes to charge 1/2 the way. Your lab will also explain what the time constant should be in terms of the resistance and capacitance of your circuit. Check that the time constant you get using T1/2 measured on the oscilloscope agree reasonably with the time constant you get by using the values for the capacitance and resistance that you are using. If these values don't agree, double check your resistance and capacitor settings and remeasure T1/2 on the oscilloscope. They should agree somewhat reasonably well. Now we will adjust the time sweep so that we can display it like it was originally, with a little bit of curvature, but still we're going to ultimately fit several periods on there. And we're also going to adjust the voltage so that it only takes up about half the space on the screen. So, setting for some curvature and then changing the frequency of the square wave, I can show a few cycles of charging and discharging. Now I will adjust the vertical positioning of this signal so it fits in the top half of the screen. I could also adjust the voltage output on the function generator. Now it's time to turn on channel 2, which is the voltage across the resistor. If we measured the voltages across the resistor and the capacitor relative to the function generator ground, both of those voltages would be measured to the left. But the oscilloscope measures the voltages across the capacitor and the resistor relative to its own ground. So the capacitor voltage is measured to the left, but the resistor voltage is measured to the right. The oscilloscope has a function where you can invert the signal on one of the channels. By inverting the signal on channel 2, we can display the resistor voltage measured to the left in the same direction that we're measuring the function generator voltage. We can do this by pressing the button under the word invert until the box is highlighted. If you don't see the word invert, press the green number 2 button. Now I can adjust the display for the resistor on the bottom half of the screen. So we look over here, we see the capacitor charge, then discharge, then charge, then discharge. The resistor voltage goes really high when the capacitor first starts charging and then goes back to 0. So once the capacitor is fully charged, there's no current flowing. Then when the capacitor starts discharging, the voltage goes really high in the other direction. But as it discharges, it goes back to 0 current once the capacitor is fully discharged. The voltage across the resistor plus the voltage across the capacitor should add up to the voltage across the function generator. The function generator has a feature called math. Go ahead and push the math button. Check that the volts per division on both channels is the same. If it's not, you can adjust it. We can also adjust the volts per division, which you can read right here, of our added together wave. On this top button over here, just turn it till you see the same volts per division for our added signal. Check over here to make sure the math function is add. If it's not, you can select it until it is. The result of adding the two voltages together should give us the same voltage that we're getting out of the function generator. In other words, we should be getting a square wave. If we are not getting a square wave, it is because there are other capacitances, resistances, and inductances in the circuit that are not being accounted for, namely in the function generator and the oscilloscope.